Section: Introduction. We're here to talk about the fascinating world of deep learning, a field that has been completely transformed by artificial intelligence. Pre-trained models have been instrumental in making advanced AI capabilities accessible to everyone. However, there's a catch. The data used to train these models is often kept hidden, leading to a lack of transparency. This is a stark contrast to the increasing availability of pre-trained models for public use. Furthermore, issues like copyright often restrict access to the original data sources. This situation calls for new ways to gather high-quality training data that can be openly shared. In the realm of vision language, the most popular model and learning approach is the contrastive language image pre-training, or CLIP. This technique learns from pairs of images and text. We think the success of CLIP models is largely due to its high-quality WIT400M dataset, which is gathered from the web. However, the exact process of how CLIP curates its data has remained a mystery, sparking curiosity in the research community for years. Some researchers have tried to replicate CLIP's data, but their methods of curation are noticeably different. While CLIP generates data based on its undisclosed data source and curation methodology, these other approaches remove noise by using the CLIP model as a strict filter. This is essentially a way of distilling the information captured in the WIT400M dataset by CLIP. The benefits of CLIP's curation process are clear. Firstly, it starts from scratch, which avoids introducing biases through filters. Secondly, CLIP's process balances the data distribution over metadata, which maximizes signal preservation while reducing, rather than eliminating, noise in the data. This balanced distribution lays the foundation for task-agnostic data, a key component of foundation models. In this paper, we aim to uncover the method CLIP uses to curate its training data. We present a study on data curation, keeping the model architecture and training schedule constant. We focus solely on the impact of training data, excluding other factors that could influence the results. We share several observations on good data quality and present a simple algorithm to make CLIP's curation process more transparent. As a result, we shed light on both the curation process and the resulting training data distribution. Our algorithm allows for easy adaptation to different data pools, enabling users to fully control their data pipeline without relying on filters from external providers. The algorithm takes a raw data pool, D, and metadata, M, derived from CLIP's queries or visual concepts, and produces a balanced subset, D*, over M, D equals F, D, M. We call our approach Metadata Curated Language Image Pre-Training, or MetaCLIP. This marks a significant step towards making the curation process more transparent and accessible. When applied to Common Crawl, CC, with 400 million data points, MetaCLIP outperforms CLIP on multiple standard benchmarks. For example, in terms of zero-shot ImageNet classification using VIT models of various sizes, our MetaCLIP achieves 70.8% accuracy versus CLIP's 68.3% on VIT-B and 76.2% versus 75.5% on VIT-L. Scaling to 2.5 billion data points, with the same training budget and similar distribution, boosts this to an unprecedented accuracy of 79.2% for VIT-L and 80.5% for VIT-H in the vanilla training setting, not using any external data, models, or longer training. We also show the impact of metadata curation on ImageNet validation plotted over training steps. First, we train on raw English data from the web, 400 image text pairs, 57.4% accuracy, then apply language identification, LID, to the random raw set, approximately 1.1 billion pairs, 54.1% accuracy. Using metadata to curate the training set, MetaCLIP 400M without balance, 60.8% accuracy, performs significantly better than these baselines, and using balancing significantly increases accuracy further, MetaCLIP, 65.5%, outperforming similar datasets, WIT400M from CLIP, 63.4%, and LAION 400M, 60.0%. The training data of CLIP differs significantly from a traditional supervised dataset in various aspects. Firstly, it involves large-scale training with mixed-quality image text pairs rather than categorized images with human annotated labels, as commonly seen in classification datasets. Secondly, CLIP's pre-training is the initial stage of training, assuming no access to previously trained models. Current research on data algorithms primarily revolves around data pruning techniques applied to well-established datasets using pre-trained models. These approaches, such as core set selection techniques, aim to select a subset of data that yields similar performance to training on the entire dataset. However, this post-hoc data pruning approach has limited utility, as the computational resources saved have already been expended during the initial training of the model. Section Summary. Deep learning has revolutionized AI, but the training data used to create pre-trained models is often concealed and lacks transparency. The contrastive language image pre-training (CLIP) model's dominance is attributed to its high-quality WIT400M dataset, but the specifics of its curation process have remained a mystery. This paper presents an empirical study on data curation, revealing CLIP's curation method and proposing an algorithm called MetaCLIP that makes the curation process more transparent and accessible, outperforming CLIP on standard benchmarks. Section: Handling noisy internet data. Dealing with unstructured internet data. Tackling the issue of unstructured and noisy data from the internet is a significant hurdle. Traditional methods often depend heavily on human-made filtering systems. These conventional techniques usually involve cleaning the dataset and removing outliers to prevent the introduction of unwanted biases into the models. Recreating CLIP's training data. Recent initiatives, such as LAION and Concurrent Work Datacomp, have tried to recreate the training data used by CLIP. However, these methods employ fundamentally different strategies for a variety of reasons. Firstly, the data used in these methods are filtered after the fact by the original CLIP model. Secondly, the data curation process in these methods depends on a labor-intensive series of filters, making it difficult to understand the resulting data distribution from the raw internet data. Thirdly, the aim is to match the quantity of CLIP's target data size rather than the data distribution itself, which could lead to an underestimation of the necessary data pool size to obtain high-quality data. As a result, the performance at the 400M scale is not optimal, with LAION 400M only achieving 72.77% accuracy on VIT-L14 on ImageNet, while the original CLIP model achieves 75.5%. The importance of understanding CLIP's data curation. The findings from these studies highlight the crucial need to understand how OpenAI's CLIP model curates its data. A thorough understanding of the curation process can provide insights into the factors that contribute to its success, enabling researchers to develop more effective and efficient algorithms for future vision language pre-training tasks. MetaCLIP. The original paper provides only limited details about how CLIP curates its data. Since crucial design choices for a direct reproduction are missing, we will clarify our choices in this section. Our aim is to uncover the data curation process of CLIP, which involves preserving the signal in the data while minimizing noise. In this section, we will explain the principles we have adopted to achieve this, which may differ from those of CLIP as these are not publicly known. CLIP's WIT400M is curated using an information retrieval method. We strictly adhere to this description and provide detailed insights into the construction process of CLIP's metadata, substring matching, inverted indexing, as well as query and balancing. Metadata construction. We begin by recreating CLIP's 500,000 query metadata. The metadata, also known as queries or entries, consists of 4 components. 1. Olson sets of WordNet. 2. Unigrams from the English version of Wikipedia occurring at least 100 times. 3. Bigrams with high pointwise mutual information. And 4. Titles of Wikipedia articles above a certain search volume. We rebuild these components from WordNet and Wikipedia and summarize the statistics in a table. We estimate the thresholds for components 3 and 4 by first choosing a pointwise mutual information threshold of 30 that meets the budget of 100K entries for bigrams and then fill the rest of the entries with Wikipedia titles. Substring matching. After constructing the metadata, CLIP's curation aligns a pool of image text pairs with metadata entries through substring matching. This process identifies texts that contain any of the metadata entries, effectively associating unstructured texts with structured metadata entries. The substring matching step retains only high-quality matching texts, automatically filtering out various types of noises that a typical filter system would consider on a case-by-case basis. Image text pair pool. We start by estimating the pool size used by CLIP's curation. CLIP's data source is unknown to us, so we use Common Crawl, CC, as the source to build such a pool and reapply substring matching to this source. We ended up with a pool of 1.6 billion image text pairs. Note that one text can have multiple matches of entries, and we have an average of 3.5 matches per text. As a result, substring matching builds the mapping from text to entry. This step has two outcomes. 1. Low-quality text is dropped. 2. Unstructured text now has a structured association with metadata. For all English text, about 50% of image text pairs are kept in this stage. Similar to CIT, this approach looks for quality matches and automatically gets rid of some type of noise, such as date strings, that a typical filter system would remove. Consider case by case. Section Summary. Handling noisy data from the internet is a challenge, and existing approaches rely on human-designed filter systems. Recent efforts to replicate CLIP's training data have different strategies, resulting in suboptimal performance. Understanding CLIP's data curation process is crucial for future vision language pre-training endeavors, and MetaCLIP aims to uncover this process by explaining the principles they adopted, such as metadata construction and substring matching. Section. Following substring matching, CLIP builds an inverted index of the data pool. All texts associated with each metadata entry are aggregated into lists, creating a mapping from each entry to the corresponding texts: B group color, cyan, $texted, entry, right arrow texted, text, $E group. As an analysis, we count the number of matches for each entry and summarize that in table. The counts exhibit a long-tailed distribution. Out of the 500K entries, 114K entries have no matches. This signifies the importance of knowing the training data distribution, since it is very likely the training data does not have certain visual concepts. We observed that only 16K entries had counts higher than 20K, accounting for only 3.2%, 16K, 500K, of the entries, but their counts made up 94.5%, 5.35B, 5.6B, of the total counts of all entries. Let's delve into the concept of inverted indexing. After matching substrings, CLIP constructs an inverted index from the data pool. This means that all texts linked to each metadata entry are gathered into lists, creating a map from each entry to its corresponding texts. To understand this better, imagine a dictionary where each entry points to a list of texts associated with it. We then analyze the data by counting the number of matches for each entry. Interestingly, we found that the distribution of these counts is long-tailed. Out of 500,000 entries, 114,000 entries didn't have any matches. This highlights the importance of understanding the distribution of our training data, as it's quite possible that certain visual concepts are not represented in the training data. We also noticed that only 16,000 entries had counts higher than 20,000. While this only represents 3.2% of the entries, these counts made up a whopping 94.5% of the total counts of all entries. We also looked at the top entries of the matching. Many of these were stop words, which don't have specific meanings but can improve the overall quality of the text. However, it's worth noting that even with substring matching, which aims to select only high-quality texts, there can still be irrelevant texts included in common entries. For example, the entry, photo, could match with the unhelpful term, untitled photo. We can address these noise-related issues in the next stage of processing. The secret sauce behind OpenAI CLIP's curation is balancing the counts of matched entries. For each metadata entry, we subsample the associated list of texts or image text pairs to ensure a more balanced data distribution. This step is designed to reduce noise and diversify the distribution of data points, making the data more versatile for pre-training. We use a threshold of 20,000 to limit the number of texts pairs for each entry. Entries with fewer than 20,000 pairs keep all associated pairs, while entries with more than 20,000 pairs are subsampled to 20,000 pairs. The selection is based on the density of information in texts. Texts with more matched entries have a higher chance of being curated. We studied the effect of this threshold of 20,000 by plotting the cumulative sum of counts for entries sorted by counts. Interestingly, the threshold of 20,000 seems to represent the transition from tail to head entries, when the head entries start showing an exponential growth rate. By applying a max count of 20,000, the growth rate of total counts is reduced to linear, which significantly balances the training data distribution. Balancing the data has three interesting outcomes. 1. It reduces dominance and noise from head entries, like common web terms. For example, out of 400 million pairs, only 20,000 texts containing photo are kept, even though there are 54 million inches photo instances in the pool. 2. It diversifies the data distribution and balances tail head entries, leading to a more versatile foundation. 3. Sampling for each entry ensures that data points with more matched entries or denser information are prioritized for curation. CLIP uses a pure NLP-based approach, requiring no access to ML models and minimizing implicit priors from humans. The metadata plays a crucial role in reducing noise and preserving signal in the data distribution. The balancing step effectively flattens the data distribution, diversifying the data and making it more suitable as foundation data for pre-training tasks. We also present an algorithm that formalizes the curation process. The algorithm aims to improve scalability and reduce space complexity for operations across data points, such as inverted indexing and subsampling. Instead of building inverted indexes, the algorithm only maintains total counts for each entry. Our algorithm approaches the balancing process through independent sampling. This avoids the need to build an inverted index that could potentially store hundreds of millions of concrete pairs for popular entries, thereby improving efficiency and scalability. Our algorithm takes three inputs: metadata, a data pool, and a hyperparameter. It aims to find a subset with a balanced distribution over the metadata. The algorithm consists of two parts, each corresponding to a specific stage of the curation process. Section Summary. In this section, the paper discusses the process of inverted indexing, where texts associated with each metadata entry are aggregated into lists, creating a mapping from each entry to the corresponding texts. The paper also introduces the concept of balancing the counts of matched entries by subsampling the associated texts, aiming to mitigate noise and diversify the distribution of data points for pre-training. The algorithm presented in this section formalizes the curation process, improving scalability and reducing space complexity by avoiding the need to build an inverted index. Section. Part 1. Entry counts from substring matching. We'll break down the complex concepts in this paper into two main parts. Firstly, we have the entry counts from substring matching. Here, we use a function called substr_matching to count the total number of matches for each entry. This count is stored in a NumPy array, where each entry is indexed by its unique ID. Each piece of text is linked to a list of matched entries. Secondly, we have balancing via independent sampling. This part is about balancing the counts on entries. Instead of creating a costly inverted index with lists of texts for each entry, we sample each data point independently. We calculate the probability of sampling each entry. Entries with a count less than a certain threshold have a probability of 1, while those with a count above the threshold have a probability less than 1. We then go through all image text pairs and sample each pair. If a pair has a matched entry that is sampled, we include that pair in our final dataset. This process is similar to the curation process used by CLIP. The chance of a pair being selected is determined by the sampling probability for each individual entry. As long as one entry selects that pair, it will be kept in our final dataset. This independent sampling approach allows us to balance each data point individually and reduces the overall operation to counting the total matches for each entry. We demonstrate this in experiments on scaling curation in a data pipeline and online balancing in a data loader. In our experiments, we collected two pools of data. The first pool contains 1.6 billion image text pairs with a total of 5.6 billion counts of matches. This pool was used to estimate a target of 400 million image text pairs, collected from 15 snapshots of Common Crawl from January 2021 to January 2023. The second pool aims to scale curation in our data pipeline. We parsed all 90 Common Crawl snapshots from 2013 to April 2023, using our algorithm to curate from a pool of 10.7 billion matched image text pairs. However, we only perform image downloading, storing, and transferring for data points that are selected by our algorithm. For training, We strictly follow the CLIP training setup, using V132GB GPUs and an equivalent global batch size of 32,768. It takes 4 days to train one model and a month to train another. We train in all experiments for the same number of iterations that correspond to 12.8 billion scene image text pairs during training. In our zero-shot image classification, we follow the standard evaluation benchmark and made sure all prompts and class names were the same as those used by CLIP. We found that our model, MetaCLIP, outperforms CLIP on ImageNet and average accuracy across 26 tasks, for 3 model scales. We also studied the effect of scaling data. We scaled data to 1 billion and 2.5 billion and observed a large gain over 400 million, with similar performance for both scales. The main difference between the two scales is the threshold, where the 1 billion set is more balanced by adding more data points to tail entries, while the 2.5 billion set adds data points to all entries. The extra data in the tail entries seems to benefit downstream accuracy for tasks on specific data, while the larger 2.5 billion data that has more head entries increases broadly over more datasets, but each at a smaller amount. On ImageNet, the 2.5 billion training data achieves impressive results. The plot shows that the 2.5 billion data is still relatively long tail, while the 1 billion data is more balanced, explaining its better performance on specific data such as bird and flower types. Section Summary. The first part of the section discusses the process of counting matches per entry using substring matching, while the second part focuses on balancing the counts on entries by independently sampling each data point. The authors demonstrate the effectiveness of their approach through experiments on 2 data pools, achieving improved performance on various tasks and datasets. Section: Ablation Study. Investigating the impact of different factors. We conducted a series of tests on MetaCLIP at the 400M scale and VIT-B32, the results of which are presented in the table. Our first area of investigation was the effect of varying the balancing thresholds, denoted as T. We found that when T was set to 20,000, as originally done by CLIP, we achieved the highest performance on ImageNet and average accuracy. When T was set to either 15,000 or 35,000, the performance was slightly lower. To further understand the impact of balancing, we trained CLIP using the entire matched pool, which consists of 1.6 billion image text pairs. Interestingly, when we increased the amount of data used for training by a factor of 4, focusing on the most common entries, the accuracy on ImageNet dropped from 65.5% to 61.9%, and the average accuracy across 26 tasks also decreased from 58.2% to 56.6%. We also found that we could apply balancing in real time during data loading by downsampling the most common entries. This approach led to a slight improvement in performance, from 58.2% to 58.5%. More details can be found in the appendix. This method is particularly useful if you have already collected a lot of common data and want to train on a different distribution. The improved accuracy with real-time balancing can be attributed to the increased diversity in the most common data.